Okay, so I have some loose ends from last time to deal with. I may not get everything done that was on the syllabus for today, but that's okay. I've got some blank periods at the end. The first thing I want to say is for the projects, I wanted you to choose by Monday, and the best way to choose is to look through the book, see stuff that's discussed in the book or referred to in the book, or download those papers that I suggested, and just, choose some more advanced topic to implement. I just thought of something else that's on the list, which would be a sort of a very minor enhancement, which wouldn't be worth too many points, is to do specular reflection in a way that's consistent with the diffuse reflection. In other words, your assignment due Monday was basically for sampling diffuse reflection. If you wanted to sample specular reflection on a Phong specular lobe and make it all consistent where you got diffuse and specular together, that would work. But it wouldn't be nearly as much points as the bidirectional reflection function, bidirectional ray tracing, or the radiance caching, or any of the other more advanced ones that actually go beyond what we discussed so far. So, just look through and think of some project and bear in mind that you're going to have to implement it. So I'd suggest if you pick something that's in one of those papers and the detail in the back of the book isn't enough for you to really see what's involved, you should download the paper and read it first before you commit to doing that specific project. And I guess you all know you can access the things like on the ACM Digital Library, any journal paper that's available through the University Library at home, too, if you use your Kerberos password and set up the VPN access. So also for the homework that's due Monday, based on a discussion I had in my office this morning, maybe there's some more clarification that I should give, but basically you're going to do the framework that was suggested on page 142 on the book, which is a sort of a summary of the different ways that you can, different routines that you would need to call. So the basic idea is, here is your eye, and I'm going to think of a single light source at the top of the room. Maybe I'll draw it in perspective. So here's a room, here's the ceiling. Our eye is somewhere inside this room. Here's the floor. We can have objects on the room. I don't know, maybe we have a table here, or say it's a box. The Cornell standard images that you probably have seen in the book just have a bunch of boxes in the room. So the kind of paths we want to be able to get, if this is the light source and this is the eye, we want paths that go directly from the light source to the eye. We want passes that go from the light source and bounce off a diffuse surface to the eye. So the first kind of path is LE. The next path is LDE. Or we want paths that they'll go from the light source, bounce off a diffuse surface, bounce off another diffuse surface, and go to the eye. And so forth, for any number of bounces. So the framework on page 132 says 42. So for eye rays, remember, an eye ray, you're going to pick a random point on the lens and trace through the point on the focal plane. So you're going to have, say, X on the lens and direction theta. So you find Y, the point where the ray hits. I think we've been calling it ray X theta. You're going to do that by ray tracing. And then use LE at Y in direction minus theta, because if you're going to hit a light source, in order to get this kind of path, you have to use the emission at this light source. You might be looking directly at a light source. So in your data where you describe the geometry for the frame, you have to specify not only the reflectance properties in terms of colors of your surface, your objects, but you also have to specify the emissive properties. Question?
Sorry, going backwards a little. You mentioned the point on the lens. Yeah. Do you want our images to show depth of field again, or is it okay if we leave that out?
You can leave that out in terms of turning it off, but I suggest leaving it in your code because, you know, for your final project, you might want to put all these effects in. But it's not required for this, but don't throw it away. Okay, so you could have just a pinhole camera for this one. In fact, in the book, this is described as the I instead of X, right? Because it's... and there we have to add on something that will get all the rest of these terms. And that's something that's called compute radians. So what I'm going to give now is the code for compute radians. And that's going to have a recursive component and a direct component. Say X direction. And so for that, you're going to return direct illumination X there plus indirect illumination. So the idea is, if this is the point X, and we have a direction that it's supposed to be returning light to, direct illumination is going to sample the light sources and get the direct illumination that's not occluded by some other objects. For example, a point on this floor here, the box would be hiding the light source, at least part of it. And also indirect illumination, which is illumination that can reach this point by bouncing from the light off of another surface to get to that point. So this is going to just trace a ray to a point on the light source using the area of the light source. And this is going to be recursive calls to this compute radiance part. So let me do direct illumination. Let's call it theta. I think they called it theta in the book. Okay, so here we have to sample a point Y on the light source. Now, the book has cases where you do multiple shadow fielders to the light source, or even choose a point among multiple light sources. So you can look for those details in the book. And so what we're going to return is the LE at the light source times the BRDF with the point X going out in direction theta and coming in direction, I guess, from X to Y. But we have to multiply it by the visibility and this geometric factor, G of X of Y, because this sample is estimating an integral over the light source of the direct illumination that's reflected toward whatever that viewing ray is looking for, this direction, theta. And what we have to multiply also is by the cosine of the nx and theta, which is just a dot product. And we have to divide by the probability density function of the point y, right? Because we're going to choose this point y according to some probability density function. For example, if it's on like a light like here, which I see has got a diffuser on it, and it's uniform radiance, probably you'd want to choose the uniformly distributed on the area of the light source. And so this probability density function would be 1 over the area. And then we'd be multiplying actually in the numerator by that area, which makes sense. Why more area should give brighter lights. And this is actually the brightness. So it's like power is the brightness times the radiance. Well, this is actually the radiance in our direction. I mean, it might not be perfectly diffuse. It may have preferred directions. So I left that off here. Okay, so that's the estimate for the direct illumination. And now for indirect illumination. So now we have to, so it's x. Direct, I think I called it theta again. At least the book does. So now we have to sample a unit direction vector psi on the hemisphere. Okay, so at this point, x here, we have some normal, and we're talking about the hemisphere above that normal. And now we have to trace the ray from x in direction psi to see what other surface we hit. And that's the surface from which we're going to be drawing the indirect illumination. So we're assuming here that it always does hit something. I mentioned cases where you contribute 0 if you sort of went out into outer space or the night sky or something without seeing any object that was going to give a contribution. And so what we'd have to do is return, compute radiance at y going in the direction minus psi toward point x times the BRDF at x going out into direction theta with radiance coming from direction psi. See, now we still need the same cosine nx psi. And when we divide by the probability density function of choosing psi. So there's no visibility function because we're just tracing out into the environment. And because we're integrating over a hemisphere instead of an area, we don't have that extra cosine over r squared that was part of this geometric factor. Actually, did I put the geometric factor in? Then I don't need the cosine here. Because this cosine was already part of the geometric factor, but the geometric factor has the other cosine in it, too, that we don't need in this case, but we do need this cosine. Divided by, again, the probability density of choosing that direction, and I'll talk a little bit more about that later. And by doing that, this compute radiance gets you a direct illumination contribution at that point y, which if it was the first call from this compute radiance, the indirect illumination part of the direct illumination part of the radiance is getting rays that start from the light source, bounce once, and get to your eye. The indirect illumination part is going to get rays that, you go from the eye to a point X, and then you go to another point Y, and the recursive call, direct illumination part of this, is then going to get rays that come from the light source. So that would get LDDE. And then the indirect part of that call at Y would get LDDDE, and so on. So by doing this enough times, you'll get all of them. But that would take forever. So basically what we'd have to say is if Russian roulette random number is greater than the R probability, this is a random number, do this, else return 0. Right? Put Russian roulette into here. It's actually in there in the book. And so that's the basic framework that you'll use to get all these different contributions. Question?
Do we have to divide by the Russian roulette?
Yeah, thank you. Forgot. What did I call it? Russian roulette probability. Threshold. It's a threshold. Thank you for reminding me. Okay, in fact, the book must have done it this way. I forgot to copy that part in my notes. So now, the other thing which I think I've said before is how to sample. What we need to do is make a hemisphere around here with the North Pole being the z-axis of the hemisphere, which means we still need to choose an x-axis and a y-axis, both perpendicular to normal, somewhere in this frame, because we need both the phi and the theta. And the phi is going to be in this xy plane. And so, given, either for each polygon, you can create an x and y axis for the polygon, or you can try and do it on the fly. So one way to do it on the fly is to say, okay, if this polygon is not exactly horizontal, I could make my y-axis be the projection of the vertical direction. Say the vertical direction is y here, or whatever it is. Why don't I just call it vertical? But if I have a vertical direction and I have a slanted polygon, and I project that vertical direction on the slanted polygon, I can find some plane that's in the polygon, from some line in the polygon. And then I could take the cross product of n and that y to get the x. That's a way of finding two perpendicular directions in the plane, and then n would be the third one. But somehow you have to find those two directions, otherwise you can't use actually, why don't I call them n, capital U, and capital V, right? And then what I can do is to sample theta and phi in spherical coordinates, and let psi equals. Okay, so what I need to do is tell you the three coordinates in the u, v, and n coordinate system. Those are like the x, y, z coordinate system. So u equal, well, why don't I say little u, little v, and little n, where u is, so here is u, v, n, that's the North Pole axis. Why don't I make it capital? These are the axes, and the coordinates names are lowercase. So that should be capital U. If I have an arbitrary direction psi, what I want to do is I want to project it onto this horizontal plane. So this is a right angle. This is a unit vector, so this length is 1, and this is my angle theta here between the vertical normal direction and psi, and that means, because this is also vertical perpendicular to this UV plane, this angle up here will also be theta, and this side opposite theta will have length sine theta. And then if phi is in this plane, actually it's all going all the way around here, or think of it as a negative angle, then in polar coordinates, if I have a radius and a phi, in this plane, I have r cosine phi along the u direction and r sine phi along the v direction. So that means r is sine theta. So I have sine theta, what did I say, cosine phi along the u-axis, sine theta, sine phi, and along this vertical axis, this length, which is the same as, the vertical component of this vector, this is the hypotenuse and this is the side adjacent. So it's going to be cosine phi. And then what we can say is that the unit vector in your world coordinate system, the XYZ coordinate system, is going to be u times this u-axis plus v times this v-axis plus this lowercase n that I computed times this n-axis. And that's how you can find your sample if you can choose phi and theta. Question?
Can I also choose phi and theta and then?
Can I choose phi and theta and then convert that into Euclidean coordinates where instead of up isn't north, up is just 0, 0, 0? Or
right, then you could do a rotation. You could apply these formulas for x, y, and z, but then you'd have to rotate the sample into a frame which had its z-axis perpendicular to the surface. In other words, in the next direction of the surface normal. Because what we want to do is, because of, in the integral, we're weighting by, another thing you can do is choose a uniform direction on the whole sphere. And then it would still be true. Then your probability density would be like 1 over 4 pi. What I'm saying is it's going to be reduced to variance if you make it proportional to the cosine theta, because at least you can cancel this factor from the numerator. I'll do that for you in a minute. So you have a choice. You can choose it uniformly on the whole sphere and then reject any sample whose dot product with the normal vector was negative. Right? Then you'd get a uniform distribution over the sphere, and you'd keep this cosine factor in here. Or you could choose a cosine. In fact, then you'd have to be the probability density, since you're throwing away things that are on the wrong hemisphere, it would be 2 pi. But I'm proposing to weight it by the cosine. Question?
Should it be cos theta for our n vector?
This one here?
The right one.
Oh, yes, thank you. Typo. Sure. Thank you. Yeah, if you look in the book, these are the formulas. They're in the appendix. How many people had seen them before I used them in class? Most of you. A couple of you anyway. Okay, anyway, look in the appendix for solid angle, and the same formulas are there. But you see why I have to put it in the... Because you you want more of these rays to go near the top of this hemisphere where the cosine contribution is higher, because ones that come in this direction have a small cosine and aren't going to contribute much to the answer. If you concentrate them where the numerator is higher, the ratio of the numerator to the denominator are more close to the same number, which means the variance is less. Okay, so how can you do that? I think I talked about that before. Basically, the PDF for theta phi, that's just called probability. That's what we've been doing before instead of probability density function, is going to be some constant times cosine theta. Okay, now I did the integral of cosine theta over the sphere, and I discovered that the integral over the whole hemisphere of cosine theta d omega of direction on the sphere was pi. And I also showed how to choose the theta according to that probability density function. So basically it's cosine theta over pi is the PDF. And so theta was cosine inverse, probably arc cosine, ARCCOS or something in C, of the square root of one random number, and phi is 2 pi times another random number, which you can get from a random number generator. We talked about doing that before. So that's what you're going to have to do to choose this direction. And then if you do it that way, then this PDF of psi is just going to be cosine theta, which is cosine nx psi, divided by pi. Right? So that means this thing is going to cancel that thing, and it's as if I put a pi in the numerator, because it was something 1 over pi in the denominator. So it's going to be pi divided by just the Russian roulette success probability. And that makes sense, because if you had uniform radiance over the whole hemisphere, then the irradiance would be the integral of that uniform radiance over the whole hemisphere with that cosine weight on it, which would give you pi times that radiance. So for constant radiance from the environment, this is a consistent answer. So are there any other questions on the homework? How many people basically already got this far? Yeah. 1. Okay, so maybe, I don't remember, writing most of what was on page 142 on the board before, so I figured I'd do that for clarity for the homework. Is there still a question?
Wouldn't that theta go from 180 to 80, and wouldn't that give you like the entire sphere and not hemisphere?
No, because I'm assuming a positive square root when I do this. And that this is only going to give you cosine inverse is only going to range from 0 to pi halves. If you wanted the whole sphere, you'd have to have a fudge where you actually had, well, first of all, you don't want, we're not doing transmission from below the patch, so we don't want the whole sphere. But if you were going to put those random points on the sphere, like I want to get back to from last class, then first of all they don't have to be cosine weighted. They just have to be, you still need that sine theta in your integration in order to get the marginal distribution for theta, but it wouldn't have a square root here, and you would have to have your r going between -1 and 1. If you were going to try and get the whole sphere. But we only want half of the sphere. So we only need to have non-negative numbers that we're taking the square root of. Does that make sense? but good question. So let me see. I want to go back to one thing I said last time that I'm not sure was completely clear is this idea of unshot radiosity. I was talking about power. My PI is the power I'm building up on all my patches. But delta PI is the unshot power that I haven't yet bounced out to the rest of the scene. Each time I bounce power to a scene, I'm getting the contributions of all the power that came in. I'm incrementing all the power that comes in the unshot radiosity. Initially, it's the original emitted radiosity from the light sources. And you shoot it out into the scene, and now you're depositing it in the unshot radiosity and all the other things. You're probably going to hit the light sources first because those are the only ones that have any unshot radiosity at all. And then after you go through all the light sources, you're going to pick the first patch, maybe, in this case, probably the floor has got accumulated most of the power. And then shoot that out into the room. And set the unshot radiosity of the floor to 0. But you still have, but you've already shot it. Okay, and then you've got some more unshot radiosity on the wall. Maybe this wall is next. Okay, so now you're going to shoot power from this wall. And you're going to shoot it in all directions, including the floor. So the floor was 0 after you shot it. But when you shoot from this wall, you're setting the wall to 0, and some more is accumulating on the floor. So after you shoot all the big walls, it may come around that the floor is the next one to be shot again. You know, before one of the small desks, the floor might get 2 shots, and so forth. And each time you shoot, you zero out the unshot one, but everything that comes in increments both this one and that one. So at any point, you're saving the amount you've got built up so far, and you can use it for rendering. So probably most of you understood that the last time. So now I want to go back to where I got flustered last time. And the problem was I wasn't reading my notes. I was trying to construct those solid angles from my usual formula for solid angles. And I forgot that I already had a formula for the solid angle of patch B. So the picture I put in my new notes had a dA on the top. So it could be like near the north pole of my sphere. And what I want to do is think of theta and phi. So here, this is a sort of a d phi. And because this d phi up here is the same as on the equator of the sphere. And I have a d phi here. And say I'm at some angle theta down here. So here's my patch dB. So it's, I guess it's something like this. So here's, say my point S was here and my point T was there. And so I also considered this sphere has radius capital R. These are all capital R's. But this sphere on which I computed d omega had radius 1. And on the sphere d omega, I had an angle here, which I called theta. Right, so let's see what's happening. So I've got some patch that's corresponding to this thing. And this is what I call d omega. What this patch dB looks like at a solid angle at this point S. And what I was trying to compute is, starting from the point S, what's the density of lines per unit d omega per unit area normal to the beam. So if I have n lines in all, say I shoot n lines by picking a random point S and a random point T on the unit sphere, you know, by the method on the last board, except instead of the square root of R1, basically it's got to be R1 itself, and it's got to go from -1 to 1. So I guess that means it's twice times a random number, drand 48 minus 1. That'll give you a random number between -1 and 1. You can use that for your theta. And random number between 0 and pi for phi, and apply those equations for a point. In that case, it would just be x, y, z on the unit sphere. You get a random one for S, and similarly a random one for T. So the number of points. So basically, the probability density for point S is 1 over the area of the sphere, r squared. No, it's 1 over the area, 1 over 4 pi r squared, because this is the total area of the sphere. And the probability density for T is the same one. So the probability density for S and T, since S and T are chosen independently, it's 1 over 4 pi r squared, right? Probability density for S times the probability for T, and the expected number say going through dA and dB. That number is what I called d squared phi before. That's the total number of lines I picked. Times, I guess it's going to be dA times dB, because this is per unit area that I'm generating them. This is the density per unit area. If I multiply it by the area, I'll get the number. And then the density per unit area, I had 4 pi r squared. So that's my K dA dB, where K is this factor here. Okay, now I want to go back to this picture and figure out if d omega is sine theta d theta d phi. That's a standard scheme of finding a solid angle in this sphere. How do I find the dB? Well, I'm going to think of it as this is, sorry, I guess this one is just r d theta, right? This is radius r, and I'm sorry, this was 2 d theta, right? Because I did this, let me do it again in my 2D picture. if I have an angle theta here, then this angle, let's see, I guess it's this angle, which is twice theta. Is that true? This exterior angle is twice the interior angle. And if it's a sine, it's the same whether I measure it this way or that way. It's still the sine. So this radius, if this was r, this is r sine 2 theta. And now if I have, this is changing by d theta, then this one changes by 2 d theta, because, let's see what's happening. Yeah, theta is increasing. This one's measured from this way as decreasing. But in any case, I guess another way to write it is it's really r sine pi minus 2 theta. They're equal. And pi minus 2 theta is actually this angle. That's increasing then by twice d theta here. So this length here is r times twice d theta. And this length here, which is sort of around, I didn't draw this exactly right. It's around a circle, but it's not a great circle, right? Its radius is r, capital R, sine 2 theta. And that's the same as sine of 2 theta is r sine theta cosine theta. So this one is r sine theta cosine theta. So dB is the product. R times sine theta cosine theta. Let's see. See, what did I do wrong? This one, I multiplied the cosine theta. This, did I? Yeah, no, this is right. That's the radius, and then I have to multiply it by d phi. Right? The radius of my circle is this much, and then the opening angle of the circle with respect to the center of that great circle is still d phi. So this one times 2 d theta. And this was, my sine 2 theta was wrong. It was 2 sine theta cosine theta. So this one is my area dB. So what I want to do now, and the point at which I got flustered last time, is I wanted to use the d omega. And I was trying to compute the d omega of B at the point S, using a distance between B and S. But really, I'm going to use the d omega that I have on the unit sphere already that I computed up here. So what I want now is basically line radians, which is the expected number of lines per unit area normal to dA per solid angle. Right? And so I'll call this L. And so that's d squared phi divided by, let's see, cosine theta dA, right? Because the dA is my unit area that they're leaving. And if it's going to be normal to the beam, I have to multiply that area by cosine theta to project it normal to the beam, like we always have been doing. And then per side angle, this is the d omega. And now in this formula, I'm going to use my d squared phi from here, which is k times dA times dB over cosine theta dA d omega. And now, in the numerator, I'm going to replace dB by the formula I had over there, which if I can see it over here, let me try and group two terms, r squared for the two r's, and then I have a 4 for the two 2's. Maybe I should put that in front, 4k. And now I have a sine theta, cosine theta, d theta, d phi. And in the denominator, I'm going to have cosine theta, dA. And then for d phi, I have sine d omega measured on this unit hemisphere, which was the mistake I was stuck with last time. I'm going to have, see if I can, sine theta, d phi. Okay, now I can cancel away happily. My d phis cancel, my d thetas cancel, my sine thetas cancel, my cosine thetas cancel, my dAs cancel, and I have 4k r squared, and that's already visibly a constant. But if I want, I can substitute the value for k I had up there, which was n over 4 pi r squared squared. So that's 4n over 4 pi why don't I say 16 is 4 squared pi squared r squared, and I forgot this r squared here in the numerator. So let me put two r squareds in the denominator, and now I can cancel one of them with this, and I have 1 over 4 pi squared r squared. Oh, n. So that's my constant. So I have verified that this method of choosing two random points on a sphere gives me a constant line radiance, at least as measured on the sphere. And now what I want to show is it's going to give me a constant line radiance measured at any point on any surface. So here's my sphere. And here is some surface inside the sphere. And I'm not going to worry about other surfaces because the way I'm tracing my lines, I continue them past intersections of surfaces. I just let them keep going because I want all the segments on all the surfaces. So let me turn pages here. So I want to follow my notes carefully so I don't mess up again. So let's assume we have some point x on the surface of the sphere, and I'm going to talk about a dA there. Did I run out of time already? I'm not even going to be able to do this part. Okay, I guess I'll be continuing with this part next time, but at least I told you more stuff. I corrected my mistake from the end of last period, and I told you more stuff you'll need for the homework, which I guess is more important. So I'll continue justifying that short paragraph in the book next time.